Okay, so welcome back, and we're going to start looking at how we interpret high resolution NMR. This is the NMR that gives us splitting as well as the regions that we see in the low resolution, which is what SL needs to look at. So let's get started. So essentially, high resolution NMR deals with how the regions split because of the way they're connected to other protons. So we're going to talk about the splitting, what we call those patterns, and what we call the N+1 rule. So essentially a high resolution NMR spectrum contains the same information as a low res spectrum, but it gives us a higher detail, sort of like taking a picture with a higher megapixel camera. All the same information is there, but we can get a bit more and we can see a bit more. So in this case, the peaks start to show a splitting pattern that provides us extra information. In this case, it provides us information about how the molecules actually connected and what protons are near each other. So each line in our low res, so you may remember the low resolution is going to have a series of just peaks, random kind of just weird humps. In a high resolution is where we start to see those spiky lines. Okay, so the number of peaks in the splitting pattern is always going to be n+1. This is our n+1 rule, so where n is the number of non-equivalent hydrogen atoms on adjacent carbons. So these are hydrogens that are different to the one responsible for giving that signal. Okay, so different to the one responsible for giving that peak. Okay, so when we look at this, there are ways that we describe these splitting patterns. We have a single line, which we call a singlet, a double line, which will be in a 1:1 ratio, which we call a doublet, a 1:2:1 ratio split, which is a triplet, a quartet, 1:3:3:1, which is 4 lines, and then a heptet, and we have a septet. We won't see heptets very often. We certainly will see septets if there's symmetry in our molecule. But what this is saying is that neighboring protons have their own magnetic field and can modify the effective magnetic field experienced by the nuclei. So remember, these are all little bar magnets, and what's happening is that the neighboring protons are interfering with the signal given by the one we're looking at. Okay, so this causes, the more neighboring protons there are, the peak is split into more peaks. Okay, so let's have a look at these hydrogens and what we mean. So the number of peaks tells us about the number of environments, just like it did with low resolution. Okay, but when those peaks are split. So if we look at this, let's just get our drawing tool up here if it's going to work. No, it's not going to work. So this guy here on the left, where we have the 2 hydrogens, okay, is going to give a singlet pattern. Okay, then the next one over, where we have the blue and the red hydrogen, because we've now put in a hydrogen, the blue ones are sitting next to a non-equivalent hydrogen. So the n+1 rule says that it will have 2 lines. Okay, then if we actually start to look at the red one is going to have 2 neighbors that are not the same as it, so it will split into 3 lines. If we come down to the middle one with 2 CH3 groups in the area, and this is where we will start to see a septet, okay, because the hydrogen is going to, the red hydrogen will see 6 hydrogens on either side of it that are the same as each other, but are different to it. So it will split into n+1 lines because n is 6. It's seeing 6 other hydrogens and therefore split into 7 lines. And then if we look at the blue ones, they will see the 1 red hydrogen that is different to them, so they will split into 2 lines. The other thing that we can look at with this diagram here is it tells us the relative area, remembering our integration tells us the relative number of hydrogens in those environments. So we can see here that from the first example it goes an area is equal to 2 because we're looking at the peak associated with the two CH2 hydrogens. Same for the next one. When we change to looking at the peak responsible for the red one, we will see that the area changes to 1. And then the bottom two examples, the septet will have an area of 1 because the peak is due to the single hydrogen being split due to the 6 on either side of it, and then the one for the 6 hydrogens will have an area of 6 and still have that doublet splitting pattern. So if we look at this with ethanol, okay, we can see with ethanol we have two clear environments here. We have the ones due to the green hydrogens and the ones that are colored red here, which is our aldehyde hydrogen. So we'd expect to see 2 peaks. We would have an integration ratio of 3:1. So because the red one, okay, is over here, it's got the C double bond O on here, it's going to actually be blocked from splitting, and then we will have this methyl here. Sometimes we can see splitting across here. It's not very often though. So one of the reasons that we see both options, okay, is essentially, if you think about it, for each of the hydrogens in that environment, they have a spin up or spin down opportunity. So when we see the hydrogen here, the green ones, looking at the red one, we can see that when the red one is spin up, it would have 1 peak, and when the red one is spin down, it would have another peak. So there's 2 ways that it can interact with it. So if we take these options, assuming splitting is going across the carbonyl, which I said before is something that doesn't always happen. Sorry, that's jumped ahead. Let's get back. What we have is that here's our external magnetic field. All the protons can be spin up and aligned with the magnetic field. We can have 2 options where we have 2 up and 1 down, just changing which ones they are, and 1 option where we have, 3 options where we have 2 up and 1 down, depending on whether it's the first one down and the second 2 up, or the first one up, second one down, third one up, or the first 2 up and the last one down. Those signals all add on top of the same spot because they're essentially the same. So we get a 1:3:3:1 option when we change the way that they lie on top of each other, which is why we see a quartet and why it will have the ratio of Pascal's triangle. So this is the triangle. So in a singlet, it'll just be 1 line. When we have 1 neighboring one, it will split into n+1 lines, which will be 2, with a ratio of 1:1. When we have 2 neighboring hydrogens, it'll be split into 3 lines with a 1:2:1. 3 neighboring, 4 lines with a 1:3:3:1, and so forth. So let's have a look at something a little bit more reasonable than ethanol and look at ethanol. In ethanol, we looked at the low resolution spectrum and we saw we had 3 regions. We have the CH3, the CH2, and the OH from that we can identify from our chemical shift and from the peak areas. When we see this in the high resolution, we'll see that the OH is on its own as a singlet, TMS down here at 0, which is just our reference peak, and then we have the triplet and the quartet. Okay, so the quartet is due to the CH2. So that CH2 is adjacent to the CH3. So its N number is 3. So it splits into 3+1 lines, which gives us 4 lines. And the CH3 sits next to the CH2. So N+1 means it will split into 3 lines with a ratio of 1:3:1, as we see here. Okay, so these fine peaks tell us what each one is connected to, therefore allowing us to get that little bit of information to confirm the assignments that we made earlier with the low resolution. So there's a couple of things to remember. that you need to note that the protons bonded to the same atom don't interact with each other. Remember, they are in the same environment, so as far as the machine is concerned, they are exactly the same. Okay, so they are equivalent and they behave as a single group. The non-adjacent carbons don't generally interact with each other. So things more than 3 bonds away don't tend to interact with each other. And if you have a large carbonyl across the group, they won't tend to couple across that either. Okay, so protons on non-adjacent carbons don't interact with each other. So we're only looking at the ones right next door when we're looking at our splitting. There are some videos here for you to watch to go through which talks about splitting a bit more, which might help, and have a look at those and see how you go. And then we've got a practice question. Okay, so we're going to look at C4H8, which is an NMR spectrum, okay, and we need to be able to look at the number of different environments, okay, so remember looking for clusters of peaks in this case. The relative number of protons, so looking at our integration values, and the splitting of each peak set, therefore the number of hydrogens on each next door carbon, so we can figure out how the compound is put together. So let's have a look. Okay, I want you to have a pause of this, see how you go in determining what we've got going on here, and then come back and look at the solution. Okay, this is going to be a little bit difficult without my pen working, but we'll see how we go. We want to look at the spectrum that we have here, and the first thing that we can see, TMS, that's our calibration, tetramethylsilane, so we don't need to look at that, which means we have 2 regions, okay? Because we've got C4H8, this means that there must be probably some kind of symmetry in my molecule, we wouldn't be seeing just the 2 regions. Then we have peak set A, which is a quartet, so this means that it is sitting next to a CH3 and it has a relative area of 1. And then we have peak set B here down at around 1, which is consistent for CH3s from our chemical shift. We can also see that it's split into a doublet. This tells us that it's sitting next to one adjacent hydrogen that is non-equivalent, so it's split into a doublet there. So we can see here it has a relative area of 3. 3 plus 1 is 4. I have 8 hydrogens to account for, which means I must have symmetry. C4H8 is an alkene's molecular formula, so I would suspect that we're looking at an alkene where we've got 2 methyl groups on either side of a double bond. So we're going to have bute, and it's going to be an ene. In order to get the symmetry, it would need to be bute 2-ene. So let's have a look at our solution. So we'll see at the way that this is written, we can see that it identifies there are 2 peak sets, so 2 different types of hydrogen environments. The peak areas show a 1:3, so for every 1 hydrogen peak set A, there are 3 hydrogens in peak set B. Okay, so if we've got a CH and there's a CH3 group, okay, because we have 8, there must be symmetry in the molecule or we don't account for all 8 hydrogens. So this is what we get from the peak areas. Then we can look at the splitting. The peak set A is split into 4, so the adjacent carbon must have 3 hydrogens on it, as we said before. Peak set B must be a CH3 group, which is consistent with its chemical shift as well. Peak set B is split into 2, so the adjacent carbon has 1 hydrogen on it. So peak set A must be a CH group, which is consistent with what we decided as well. Looking at the data booklet, we can use the chemical shift to identify the groups and find that the 5.6 is definitely consistent with a CH attached to a CH group by a double bond. And then peak set B 1.7 is consistent with a CH3 attached to a double bond CH group, which gives us the solution that our compound is actually bute 2-ene. Another example question for us to look at. This time we have the integrals as the lines above the peaks, okay, and it's C2H4O. You need to deduce the molecular formula of the compound, draw possible structures of the molecules, and then use the data book to identify which one is which. Pause the video and have a go at this one. Let's see how you went. Hopefully you have managed to pull out all the relevant information from this structure. If we look at the solution, we can see that it had 8 hydrogens, so it must be C4H8O2, okay, and we have a 2:3:3 ratio. We have an IHD of 1, so we must have a ring or a double bond present as well. When we draw out all the possible structures for this molecular formula, then, remembering that we have 2 oxygens, so it opens up the possibility for carboxylic acids and esters, okay, we can get a number of them where we start to see straight away that the data doesn't fit some of them. So if we're looking at a carboxylic acid or an ester, the first thing that we're going to see is that we don't have an OH acid shift from our chemical shift, but we do have 3 environments. So we would go through all these structures, narrow down which ones have 3 environments. Chemical shift of 1 to 1.5 with an integration of 3H is always going to be a CH3. We can see it has a triplet splitting pattern, so it must be sitting next to a CH2. Then we can see down here at 3.8, 4.1, we can see the CH2 of an ester, okay, with a 2H integration, split into a quartet. So this is that CH2 that was attached to the CH3. And then at 2 to 2.5, we have this upshifted CH3, okay, so sitting much higher than a normal CH3, as a singlet, so we know that it's on its own. So because we have the CH3 into the carbonyl, that tells us one side of the ester. The OCH2CH3 gives us the other side of the ester, and we can see that we actually have ethyl ethanoate as the structure. Hopefully you came up with that. If not, have a look at how the justification is done and see if you can follow it. These are some exercises to do from your textbook. Hopefully now this is making a bit of sense. Remember, it is practice and getting used to these patterns. So good luck.